Hi, my name is Ravi Kumar T, Assistant Professor, Department of Mechanical Engineering, SVIT, Bangalore. So today I am here to explain in Applied Thermodynamics, Module 5, Part B. In Module 5, Part B means it's a steam nozzle. Okay, so we shall see what is a steam nozzle. So this nozzle, okay, so nozzle, it's a varying cross section. So varying cross section which is used to convert the heat energy of the steam. Okay, heat energy of the steam to a kinetic energy. Okay, now so what is the use of this nozzle? So the major function of the nozzle is used to increase the high velocity of the steam, okay, and which is used to drive the turbine. Okay, so which increases the high velocity of the steam, but which is used to drive the turbine. Okay, so then what is another very important thing is in the nozzle. So in the nozzle there is an increasing velocity, but there is a decrease in pressure. Okay, increase in velocity and there is a decrease in pressure. So that is the main function of the nozzle. Okay, so in the nozzle there are many types of nozzle. There are three types of nozzle. So first one is convergent nozzle, divergent nozzle, and then convergent and divergent nozzle. So what is a convergent nozzle? So you can observe convergent nozzle. See, convergent nozzle here, in the main thing you have to remember is the area is gradually decreases from front of the nozzle to a end of the nozzle, means entrance of the nozzle to a exit of the nozzle, means area is gradually decreases. So if it is so, where are you going to use this type of nozzle? That is another question. So you are going to use this nozzle where the back pressure is equal to or greater than the critical pressure. Okay, so in this condition where back pressure is equal to or greater than critical pressure ratio, where this condition is applied, so where you're going to use this type of nozzle. This is convergent nozzle. Then what is a divergent nozzle? So divergent nozzle, here in the divergent nozzle the area is drastically increases from entrance of the nozzle to a exit of the nozzle. Okay, so where are you going to use? See, these two are very important. Convergent you're going to use back pressure is equal or greater than the critical pressure ratio, but divergent you're going to use where back pressure is less than, you can observe, is less than critical pressure ratio. Okay, so we'll see what is another type. So another type is what? Convergent and divergent nozzle. Convergent and divergent. See, okay, convergent and divergent, here you have to remember three different parts are there in the convergent and divergent nozzle. Which are the three different parts? One is a convergent part, throat part, and divergent part. See, convergent means you already know area decreases. Divergent means you already know area increases. Then in between you will be having a one separate part, that is a throat. Okay, so in the area, in the nozzle there is an increase in velocity and decrease in pressure, but while in the throat, so there is no increase in pressure. Okay, it maintain constant. Okay, so this is the convergent and divergent nozzle, and this type of nozzle you're going to use in almost all the applications. You're going to use a convergent and divergent nozzle. Okay, and here you have to remember there are very important thing is the steam flow through a nozzle. So in the nozzle, see, if you consider nozzle, it is an open system. Okay, open flow system means mass and energy can easily transfer the boundary. Okay, so since it is an open flow system, so we must understood that there is no heat transfer. Okay, so there is no heat transfer or heat gain or heat loss to a surrounding or from the surrounding, that we have to remember. If there is no heat loss, it understood that it is a adiabatic flow. Okay, if adiabatic means you should remember that there is no there is a entropy remain constant and only a work done. Okay, only a work done if entropy remain constant and there is no heat transfer. Yeah, I will go one by one. So frictional less adiabatic flow. See, in frictional less adiabatic flow, the expansion of the steam in the nozzle, neither heat is supplied nor heat is rejected. So that is called as adiabatic flow. So in this time, the nozzle work is performed without considering the friction. Okay, frictionless you are considering. So here without considering a friction. If there is no considering a friction means the kinetic energy will be drastically increases. If you consider a friction, there is an increase in entropy and there is a decrease in efficiency or there is a decrease in work. Okay, yeah. So since it is adiabatic and frictionless flow, okay, adiabatic and frictionless flow, the entropy remain constant. Okay, so we'll see how you can represent this. See, you can represent the in HS diagram. See, this is a saturation curve. Okay, I'm considering point 1 and the saturation point. Okay, then as you know, the pressure is decreases. So pressure is decreases and entropy remain constant because it is adiabatic flow. So entropy remain constant. This is how you can represent. So similarly, frictional adiabatic. See, as you know, if you consider a friction, there is an increase in entropy. Yeah. See, 1 to 2 is your what? Frictional flow, means without considering friction. If you considering friction, you can observe a dotted line. So there is an increase in entropy. Okay. So here, as I said, entropy increases, energy decreases, velocity at the flow throat is decreases, then volume of the flow steam is decreases. So efficiency decreases. Yeah. Next, last is saturated flow, super saturated. See, if you work in a super saturated flow, automatically your efficiency of the system will increases. Okay, because you are supplying more than the 100 degrees Celsius. Okay, 100 is a saturation, you are supplying more than that, it is a super saturated. Okay, so yeah, the steam expands in the nozzle, pressure and temperature in it drop, reduces. Okay, and it's likely that steam start condensing when it strikes the saturation line. So this is not always situation for throughout the nozzle. There is some different situation, there is a nozzle. What are the different situation? See, you can observe, due to high velocity, the time up to which steam resides in the nozzle is small, and there may not be a sufficient time for needed heat transfer and the formation of liquid droplets due to condensation. If the condensation is delayed, okay, for a while phenomenon, this is called as a supersaturation phenomena. Okay, so this you can represent here very easily. See, you can represent like this. See, the point 1 is supersaturation line, okay, above the supersaturation, and point 2 will be within the saturation. Okay, so this is how you can represent a supersaturated flow. So this is very important question in exam. So many times they ask to explain the supersaturation flow in the nozzle. Yeah, so next is a velocity. Yeah, so velocity, you have to find out velocity. Okay, so to find out velocity, there is a there is a increase very less velocity and exit will be a more velocity. Okay, similarly, how you can define velocity? See, you have a formula that kinetic energy gain is equal to adiabatic heat drop. So kinetic energy means, as you know, yeah, C will be as velocity, okay, H will be enthalpy. So C2 square minus C1 square by 2 is equal to H1 minus H2. So you take C2 2 into 1000, H1 minus H2 plus C1 square. Why 1000? Because H is in kilojoule. So H is in joule, so it will get you will get it in terms of if you convert, you will get it in terms of meter per second. Okay, if C1 is neglected, initial velocity is neglected, so you'll get C2 is equal to. Okay, so very important derivation in the nozzle. So we'll continue. So this discharge through the nozzle and condition for its maximum value. So this is very important derivation. So for here you will consider P1 is the initial pressure of steam, V1 is the initial volume, P2 is pressure at the throat, V2 is a volume at the throat. Okay, so area is cross section at the throat, C2 velocity at the throat. Clear? So next we'll consider, so to find out this nozzle, as you know, it is it's adiabatic flow, okay, polytropic flow. So that's why we'll consider PV power N is equal to constant. The value of N for saturated flow is 1.13 and for superheated is 1.3. Okay, so for this is very important. So work done, okay, so work done per kg of steam, during the cycle you'll get, so work done is equal to N by N minus 1 P1 V1 minus P2 V2. Okay, P1 V1 minus P2 V2. So this you can take it as a very important equation in the nozzle. So therefore in the nozzle, you know, gain in kinetic energy is equal to adiabatic heat drop or work done. Okay, adiabatic heat drop or work done. So gain in kinetic energy, if you neglect the initial velocity, you'll get c2 square by 2, and what done is n by n minus 1 p1 v1 minus p2 v2. Okay, so you can take p1 is a common, so 1 minus p2 v2 divided by p1 v1. Okay, again see p1 v1 power gamma is equal to p2 v2 power gamma, sorry, n. Okay, adiabatic polytropic index. So you know also. So next is, yeah, you can take v2 by v1 is equal to p1 by p2 power 1 by n, or v2 is equal to v1 into p1 by p2 power 1 by n. So this equation you can take this as equation number 2, and even you can take equation number 3. Okay, so yeah, now what you want to do, you have to substitute. Okay, you have to substitute equation number 2 in equation number 1. Okay, so we get equation number 2 in 1, we get c2 square by 2 is equal to n by n minus 1 p1 v1 1 minus p2 by p1 into v2 by v1 power 1 by n. Okay, so next n by n minus 1 p1 v1 1 minus p2 by p1 power n minus 1 by n. Okay, I'm sorry, this is not a pv, this is a p1, this is p2 by p1, I'm sorry, p2 by p1. Okay, so next is c2 square is equal to 2 into n by n minus 1 p1 v1 1 minus p2 by p1 power n minus 1 by n. Okay, so next is c2 square means c2 square root 2 into n minus 1 p1 v1 is equal to 1 minus p2 by p1 power n minus 1 by n. Okay, so next here you can take this equation number 4. Here is very important thing, you have to differentiate. See, if m is a mass of steam discharged, in kg per second, then mass is equal to AC2 means area into C2 velocity divided by V2. Equation number you can take 5. Okay, so now substitute equation number 4 in equation number 5, equation number 3 and 4. Okay, equation number 3 and 4, previous equation, and 4 in 5. So like mass is equal to area. Okay, fine. What is V2? So you already know V2 is equal to what? P1 divided by 1 power n. So similarly you have to substitute here. So P2 divided by P1 power by n, and then C2 value is here, so you substitute C2 value. So square root 2 into n by n minus 1 p1 v1 1 minus p2 divided by p1 n minus 1 by n. Okay, so now you have to simplify. Okay, so by simplifying you'll get a by v1 into square root of 2 into n by n minus 1 into p1 v1 into p2 by p1 power 2 by n minus p2 by p1 power n plus 1 divided by n. Okay, if you simplify you'll get this. Okay, so now you have to differentiate above equation, differentiate above equation with respect to critical pressure ratio, with respect to critical pressure ratio, that is P2 by P1. Okay, P2 by P1 and equal to 0, and equal to 0. So therefore you'll get, therefore d by dp P2 by P1. So only the P2 by P1 only is equal to 0, others are not equal to 0. So that's why I will not consider that. I'll consider only P2 by P1. Even square root is also not equal to 0, so that's why I'm not considering it. P2 by P1 n plus 1 by n, so and equal to 0. Okay, so now you have to simplify and you have to differentiate and you have to simplify. So how? Okay, you can observe how. You see, if you simplify it, you'll get 2 divided by n into P2 by P1 power 2 by n minus 1. So this is the differentiation of first term. So next is what? N plus 1 by n P2 by P1 n plus 1 by n minus 1 is equal to 0. Okay, so now if you simplify it, you'll get P2 by P1 minus n divided by n. Okay, so is equal to, means if we go to that term, okay, see 2 by n here, n plus 1 by n into n by 2. See, this 2 by n will come to this side. So then P2 by P1 power n plus 1 minus n divided by n. Okay, okay. So now this is get cancelled and this n is get cancelled. Okay, so next P2 by P1 only 2 by n I'll take is equal to n plus 1 by 2. Okay, so this n will be, if shifted to this side, means I'll get P2 by P1 1 by n into n. Okay, so this is n get cancelled. You'll get P2 by P1. Okay, if it come this side, you'll get again 2 minus n. This is plus 1 is there, so you'll get minus 1. If it come left hand side, so you'll get P2 by P1 power minus 1. So that's why you'll get minus 1 plus 1 by 2. Okay, so next you'll get P2 by P1. Okay, so P2 by P1 you'll get minus n. Okay, sorry, 1 minus n. You'll get 1 minus n. So and you will be having a power n. Okay, so means this n is also multiplied here. Okay, it will also multiply here, so you'll get power n. Okay, so you'll get n plus 1 by 2 power n. Okay, so next is, you can observe. Okay, so next is, if it P2 by P1, if it go to that side, you'll get n plus 1 by 2. Okay, n plus 1 by 2, you'll get n into minus 1 by n. Okay, if it go to that side, you'll get minus 1 by n. Okay, so next you'll get okay, P2 by P1. Okay, now n plus 1 by 2 power n minus 1 by n. Okay, so next is, you can write P2 by P1 is equal to n plus 2 divided by n plus 1. If it replace here, you'll get n by n minus 1. So this is the critical pressure ratio formula. Okay, okay, so very important formula to be used in this chapter. So first is velocity. Okay, so C2. See, this C2 will be used if only convergent and divergent is used. So that there you'll get 2000 into h1 minus h2 plus c1 square. If c1 is neglected, if c1 is equal to 0, you'll get c2 is equal to square root of 2000 into h1 minus h2. Okay, so for convergent and divergent nozzle, you'll get C2 is velocity at throat. C2 is velocity at throat and C3 is velocity at exit. Velocity at exit. So here you will be having formula 2000 into H1 minus H2, and here you will be having formula 2000 into H1 minus H3. Okay, and here you will be having a formula A2 is equal to m C2 divided by V2. V is a specific volume, and here 3 is equal to m C3 divided by V3. Okay, so next pressure ratio formula is what? P2 by P1 is equal to, so this is 1 and this is 2 and this one is a third one. Okay, P2 by P1, 2 divided by n plus 1 power n by n minus 1. Okay,